So it's great to be here for the first time on the 20-meter antenna. Thank you, Peter, for inviting me. It's been a pleasure to meet all of you. Let's get it started. I'm going to talk about amateur decoding and reception of deep space probes and satellites, especially the work we've been doing with Bochum Observatory during the last few years. So just to recap, the deep space communications are done for three things. One is telemetry, which is sending data from the spacecraft back to Earth. The other one is telecommand, which is sending information, mainly commands, from Earth to the spacecraft. And the third one, which is also quite interesting, is ranging or navigation. That means figuring out where the spacecraft is, because you need to know that to plan maneuvers, to plan ahead if you want to land on Mars, where you actually will land. And as you can imagine, you do not have GPS out there in deep space. You can have GPS on high Earth orbits. We heard about this morning. You might also have on the Moon. That's an ongoing topic of research, but definitely not on Mars. So you do navigation. The frequency bands, 8.4 gigahertz, which is X-band, is the most common for older missions or also for Moon missions. You can also use S-band, which is kind of simpler to set up and doesn't suffer so much from rain fade. But now the trend is going to higher frequencies because people want more data bandwidth, and that means more gain on the antenna, so higher frequencies help you do that. And for that there is Ka-band for deep space, which is 32 gigahertz, and K-band for near Earth. And near Earth is anything within 2 million kilometers from Earth, so that's the Moon and also the Lagrange points. So for example, James Webb Space Telescope is near Earth. It does 27 gigahertz or 26 gigahertz to send those beautiful images we have all seen. As you can imagine, if you're deep out in space, in Mars, Jupiter, or whatever, or even Voyager 1, the free space path losses are very, very large. They go with the distance squared, so you need very large antennas on ground. Professionally, they use anything from 30 meters, so 32, 34 meter, up to the 70 meter antennas that NASA uses. And to get global coverage, both NASA and ESA, they have their ground station network, which is 3 sites on different parts of the Earth, and that gives them global coverage. China also has a pretty decent deep space network, and other nations such as Japan, they have 1 or 2 ground stations and they collaborate with either ESA, NASA, or whoever. So as you can imagine, interagency cooperation is a huge thing, because if you're running a mission and there's a critical thing, like we're landing on Mars, you do not want to depend on just one ground station. So you might have a NASA mission and ESA is also covering the same mission, just in case there is bad weather at the NASA ground station. That might happen. And for interagency cooperation, you need standards, you need documentation. So luckily for us, a whole bunch of documentation is publicly available online. This is free. You do not even have to register. I have some references in there about key things you can Google. And also, usually you have the ephemeris available online. The ephemeris are the trajectory of the spacecraft, so that gives you the indication of where to point your antenna if you wanted to track the spacecraft. And there is a online platform which is called NASA Horizons, and there you enter ground station location, the name of the spacecraft, the date, and it will give you azimuth and elevation and much more information if you need. So the information for ESA missions, for NASA missions, and from other nations is on the platform. For Chinese spacecraft and for some Indian spacecraft, it's not available on the platform. I think it's just lack of communication channels to get the information where it should be, rather than a desire for secrecy on those missions. But anyhow, there is also the DSN Now webpage and the STRAC Now webpage. They will show you what ESA and NASA are tracking at the moment, with various levels of technical detail, and they keep dropping in technical detail because of security constraints. Until a few years ago, amateur radio operators had small antennas at home, maybe 1 meter dish, 2 meter dish, maybe 3 or 4 if you're extremely lucky. And with that, you are able to detect the weak carrier signal of one of these deep space missions. Because most of them, their signal has a spike in the middle. If you imagine an AM signal, it has the carrier spike, and then it has some bunch of modulation. So it's the same for most DSN signals. They are phase modulation rather than amplitude modulation, but it works in a similar way. So you have this carrier, and if you imagine the signal drops down in power, drops down because your dish is small, eventually you just see a tiny carrier and nothing else. So you can detect the spacecraft. You can, hey, it's a great project to do. I have my ground station at home. I can detect Mars missions. That is great. But nowadays, I think two main things are happening. We have more launches. So when there's a launch, the spacecraft is going to be near Earth for at least a few days. There are more launches to the moon, and the moon is not so far. And also, we have large facilities. So there's Bochum, which has been around for quite a long time, but recently the number of deep space tracking activities in Bochum has increased. And also we have Dwingelo. I do have that on another slide, so I will get to it. So we have more large ground stations which are able to track deep space missions. And then what happens is people are starting to decode or demodulate this telemetry. So basically, as I was mentioning, until now the challenge was really more on the hardware side of things. You need to make your own X-band receivers because off-the-shelf hardware is really, really expensive because it's just a niche application. And with that, people could detect signals as far as Jupiter or Saturn. That is like standard thing. Or even with some effort, Voyager 1. We saw the detection of Voyager 1 with Bochum, but it can also be done with 6-meter dishes, and Luis Cupido did that in the early 2000s with a 3-meter dish, I believe. So something that with a well-tuned system, if you observe for long enough, even today, I think it could be done with 2-meter dish, 3-meter dish, whatever. But going on with the decoding, as I was saying, there is a recent trend because there are more deep space launches that gives opportunities when the spacecraft is close to the Earth. Also flyby, so many of these missions, they will launch and they will do a gravity assist on Earth, so that gives you another opportunity to observe the spacecraft when it's near. Moon missions and collaboration with Bochum Observatory, the 25-meter telescope in Dwingelo, which is managed by cameras. It's an amateur society, and also the Allen Telescope Array in California, which is an array of 42 6-meter dishes. Not all of them are operational. I believe about 25 of them are operational at the moment, and this is managed by SETI Institute, which is a private organization devoted to searching for extraterrestrial intelligence. And then also something that has happened is the boom of software. We have gone into this software stage of history where software is available online, and if you want to do something, you can just download the software and do it, and it's free. And the only difficulty is maybe you need to install the software, maybe you need to learn how it works, but that's something you can do. And I've been doing software in Geo Radio for all these missions since I started a few years ago. Alan, who's there recently, has been adding support for deep space missions to SAT-dump. So these are probably the two widely available pieces of software. And then there's a man from Czech Republic who goes by the name of Root. He has been doing a lot of deep space decoding in the past, so he has decoding software. This is not widely available, but some people have used it. So if you reach out to him, maybe he can give you a copy of the software. So I started back then in 2020, so that's 3 years ago by now. And what happened is Paul Marsh got in touch with me and he said, I've made a few recordings of Solar Orbiter and Bepi Colombo, which are two ESA missions. Solar Orbiter was just being launched at the moment. Bepi Colombo was on a gravity assist. And he told me, I have these recordings, would you be interested in looking at them and playing with them? And I came from a background of doing small satellite decoding. I lead a project which is called GR Satellites, which is radio decoders for amateur satellites. And said, why not? Let's see how this is any different from small satellites. And I made some radio decoders for this. And basically, I kept continuing doing this for all the missions which have been launched since then. Something that happened at the time was Corona. Not surprisingly, that meant we all had more time than usual to be at home playing with the hobby. So that was really what kick-started my activities with deep space decoding. I had these recordings, I had more time, and I got quite interested. And also what happened during this year was 2020 was a big launch window for Mars. There were 3 Mars missions launched. One is Tianwen-1 from China, the other one was the Perseverance rover from NASA, and the third one is Emirates Mars mission, so the Hope probe from the United Arab Emirates. They all launched in the summer of 2020, and especially Tianwen-1 was very interesting because the trajectory data from Tianwen-1 was not publicly available, but we discovered it in the telemetry fairly soon, a couple days after it launched. So this became an exercise in if we continue to track this spacecraft, we will get updated trajectory through the telemetry so that we will be able to continue tracking the spacecraft, because with a large antenna such as Bochum, the beamwidth is rather small, and if you don't know exactly what the spacecraft is, then basically you lose it. So this was very interesting, and also something interesting is that this spacecraft is pretty loud. Compared to other Mars missions, is by far the loudest. It also transmits less amount of data. The data rate is lower. But it's pretty loud. It's loud to the point that people, so for example, Paul Marsh, on the last Mars close approach to Earth, so that's 40 million kilometers, I believe, that was on the winter last year, he was able to decode with his 2 meter something station at home. That's really a huge thing. Figure out 40 million kilometers, Mars probe, guy dish on his backyard, telemetry. So, okay, Tianwen mission, I could spend a whole talk talking about it because we did so many things. Basically, we've been tracking the spacecraft with the Bochum antenna at least for a few minutes or a few hours every day, because usually the antenna is busy tracking stereo A, but whenever it's not busy and there's time, it can go on track Tianwen-1. So mostly daily we have been collecting telemetry from Tianwen-1 since launch till now, and you have the dates there. So it's already more than 3 years worth of data, of trajectory data, but also telemetry data we have collected. And that is really amazing. The system is mostly automated to this date. There is like a script thing that grabs the data, copies it, and then I basically get an email daily with a summary of the orbit trajectory to check if our trajectory information is still accurate enough, if there have been any maneuvers of the spacecraft, and there haven't been any in years. But I mean, this is a first event that an amateur facility such as Bochum is tracking an object with professional capabilities. I guess it's also the same with stereo A, but stereo A is a network of ground stations, and if Bochum is not there, Kiel will cover or something, but Tianwen-1 is just Bochum, and it's the system and keeps running, doesn't fail. So we even published a paper on the GNU Radio proceedings, because all this runs on GNU Radio with Mario and Peter, And something important that happened during the mission is the live stream, the YouTube live stream by AMSAT-DL. That was huge because something that China doesn't do particularly well is outreach. Even to the Chinese citizens, they were very engaged and very proud and interested that, hey, a spacecraft from China is for the first time landing at Mars, but they didn't have like live broadcast or that thing. They had the YouTube live stream from AMSAT-DL, and there were a bunch of Chinese people, comments on the YouTube chat. There was even Phil Karn some days, so it was technical chat mixed in with people really proud and happy. It was great fun seeing this all in real time unravel during the landing, the key maneuvers. And this is the live stream. This is during the landing. What you can see here is on the bottom, I think there is laser pointed, yeah, on the bottom, this is the usual low data rate telemetry. The telemetry is here. This is the carrier I was mentioning, so I don't know if it can be seen on the spectrum, no. But if you think of the spectrum, this is a sharp peak. If you were to have a small station, you only see this peak. If you have a large dish, you can also see these side lobes where the data is and collect the data. So basically this was during part of the landing. I don't recall exactly which moment. What happened is for the release of the rover, the spacecraft needed to rotate, so that means the high gain antenna is no longer pointing to Earth. And then the rover is released, the spacecraft turns again to point to Earth. That is when we recover the signal. So when this was taken, the spacecraft is pointing again to Earth. And of course, even the Chinese with their larger antenna, they have lost some telemetry while the spacecraft was pointing away from Earth. So what they do is switch over to some higher data rate, and they download this as a playback of data. This is the Tianwen-1 orbital parameters. So this is all done with data collected at Bochum. Basically, these are all data points from the telemetry recorded here. They are interpolated using propagation in GMAT, but all this original information from Bochum. And you can see here the dates. So this is just the what is called the remote sensing orbit. This is the last mission phase. It's the current mission phase because the mission is still going, but it has met all of its science goals. So since the beginning of 2022, even the end of 2021, until today, we have almost continuous data. And you can basically see how the orbit parameters change. So for example, you can, this is the latitude of the periapsis. The orbit is elliptical, and the periapsis is the point where it's closer to Mars. And you can see it's going from the North Pole to the South Pole, then from the North Pole, South Pole again. This is because of orbit perturbations, of the sun's gravity, the fact that Mars isn't perfectly spherical, but they have done this on purpose. So what this allows them is to cover from a low height, from the periapsis height, all the surface of Mars. They keep scanning, and within a year or whatever, they will move from being above the North Pole, very low, to being on the equator and down at the South Pole. So with that, they have collected a high-resolution image of all Mars. What else did we do back then? So I have mentioned the HOPE probe, Emirates Mars mission that launched in July 2020. And AMSAT-DL was live streaming the Mars orbit injection. So as the spacecraft is coming near Mars, it will engage its thrusters to basically get captured by Mars gravity and enter orbit in Mars rather than just swinging by. And it was just the live stream, so the only data we have recorded for this is the live stream images and the live stream audio. But you can use the live stream audio, so this is what I did. And maybe you can see it here. You can see this diagonal line, maybe here, and if you believe me, there's another one, another one, another one. So what's happening here is this is the carrier from the spacecraft, the RF carrier. During the maneuver, it was also pointing away from Earth, so we only see a weak signal, even with Bochum. And then there is this Doppler correction algorithm at Bochum, which for some reason works in steps. So what happens is the frequency comes down, and when it goes past some point, basically you tune a notch down, and so the frequency comes back up again and comes back up again. And it's quite difficult to make some sense of this. So what I did was to correct by hand. And all those jumps, basically I have glued them together. So now we see the signal is completely flat. I have also corrected for the slope. And this is before the burn began. So basically this means constant acceleration caused by Mars gravity. And at this moment it's beginning to burn, so it's beginning to thrust. And the difference in slope here is just the acceleration caused by the thruster. This is just with the audio from the live stream, so you can imagine there's audio compression in there, lossy things and whatnot, but even you can do some measurement here for how long they burned, how much thrust they had, how much delta V, so the change in velocity. And it would be even better to have had IQ for this. With IQ, more analysis can be done. What else? Another Chinese mission by the end of 2020. This was the Chang'e 5 sample retrieve mission, a moon mission which landed on the moon, collected some lunar soil samples, and then flew back to Earth and returned the capsule with the samples. So most of the tracking I did was with the Allen telescope array, but with Bochum one day, Achim Volhard caught the lander on the lunar surface, sending high data rate data. So that's 5 megabits per second worth of useful data, most of which we could decode. Unfortunately, it was mostly idle data, so what happens is they engage this high data rate signal. When they see that the signal is stable, they command transmit whatever files they want to retrieve, and then they keep it running for a little while. So unless you are lucky and get it to record exactly when the file transfer happens, which can be pretty quick, you just get the signal which is wide and pretty fast, but it only carries, or it mostly carries idle data. So it was only idle data, nothing interesting here, but I think that's a major goal, 5 megabits per second from the moon, 40,000 kilometers being received and decoded correctly here on Bochum. More recent stuff, also moon missions. So the end of 2022 was hot with moon missions because we had Artemis 1. With Artemis 1, a bunch of CubeSats were also launched. I think Bochum also tracked a few of those. In fact, in putting together this presentation, it was difficult to do because we've been tracking so many things, and information is scattered, it's in tweets, it's wherever. So I went through my blog and got some of the most interesting details, but I've missed a bunch of the stuff which was only on Twitter or random remarks or comments. So anyhow, Artemis 1, and after Artemis 1, 1 month after Artemis 1, there was this SpaceX launch with Lunar Flashlight, which was an NASA spacecraft that didn't make it to Artemis 1, and Hakuto M1, which was a private Japanese moon lander mission. And then this is basically one of the radio applications or flow graphs I make, so you can see a little bit of the technical details. What is happening here is this is the spectrum of the signal, and this is after a PLL, so after phase locked loop. With these signals where you have this carrier, you usually have the phase lock loop to lock to the carrier, and then basically what happens is this carrier is your phase and frequency reference. You will find it on the I, so you have I and Q data, you will find it on the I, and on the Q you will find whatever telemetry modulation, whatever data is on the signal. So here you can see these two side lobes, and this is symmetric, and they carry the same information. It's similar to AM, it's phase modulation again, but BPSK, you can think of this as a standalone BPSK signal on a subcarrier. And this is the BPSK constellation. So if you have ever seen a constellation diagram, this cloud of points stands for some bits 1 that were transmitted. This cloud of points stands for some bits 0 that were transmitted, so digital information. And since you get noise on the signal, the cloud of points spreads away from the ideal location, which is here and here, and they mixed together a little bit. So anytime a point crosses over, that means it's a bit error. You are basically flipping one bit on your receiver. There are error correction codes to account for that, and that's part of what the software we have been making does, to run these error correction codes to fix these errors. But this is pretty good. Even with a worse constellation, you can get all the errors corrected. And here is time domain diagram. Maybe it's not so easy to see, but here are some red spikes, if you believe me. Those are the start of each frame. So there's a synchronization word which tells you where each frame begins. So by looking at all of these, you can assess the signal quality. You can even do that in real time and figure out if there are some parameters you need to tweak in your decoder or your system, or if the signal is weaker or stronger than usual for any particular reason. So what can you pull from the telemetry? I was mentioning trajectory data from Tianwen-1. That's the only mission we have been able to do that, and it's slightly unusual because if you think there's no particular reason why a spacecraft would be telling Earth why the spacecraft is. It's usually the opposite way around. It's Earth which is telling the spacecraft, you're now at this point, this is your trajectory, so if you need to point antennas or if you need to do whatever, you know where you are. But for some reason, Tianwen-1 had this information in the telemetry. It was sending its own trajectory back to Earth. We believe that maybe since there was a prototype for an optical navigation system on board this spacecraft, it had something to do with it, but we never knew for sure. Why is the reason? But something you have in most spacecraft is attitude. We have heard about Arminas, the attitude sensor on board. Most spacecraft have attitude sensors on board, and the main information you get out of an attitude determination system is something which is called quaternions, and that's a somewhat complicated mathematical object that tells you how you are rotated in space. If you pick something like this, which has 3 different axes, and you choose an orientation, there's one quaternion to describe that orientation, and basically if you are like me, who has no proper spatial orientation, you can play at home with some object and try to see how the math relates to this, and hey, it is turning like this, and so on and so forth. So just mathematical object to figure out how something is pointing in space. For some of the missions, we can find these quaternions because they are 4 numbers. They have norm 1, which means if you square all of them and sum up, they should add to some constant, which if you normalize is 1. So that makes them slightly easier to find out in just the mess of numbers that is telemetry, because if you have spacecraft telemetry and you don't know this specific format, it's usually a custom format for each mission, then you're just looking at a bunch of numbers. You might plot a few of them and recognize some of the patterns, like maybe this looks like something is heating up and then cooling down, so maybe there's some temperature and there's some heater trying to keep the temperature within some levels. But this is the way we try to figure out what's in telemetry. So quaternions is more simple to figure out that something you're looking at is quaternions. And this looks like some wavy things, so some sinusoids. But if you do some calculations, What you can do with the quaternions is here in orange, is the angular velocity. So the angular velocity tells me how fast something is rotating, like this. And there's also gyroscopes, mostly present in any attitude and determination control system. So you can also find gyroscopes because those are 3 numbers. You usually have gyroscopes in 3 different axes. And also the gyroscopes describe your angular velocity. So if you find out that you have 3 numbers that describe roughly the same angular velocity as quaternions, so you can see here the same graphs, then those are your gyroscopes. And as you can imagine, the gyroscopes are more noisy because in computing these quaternions there is some filtering or some processing, and gyroscopes is just the raw data. So we can keep processing this. With the quaternions we can know the absolute attitude. The gyroscopes only tell you this is rotating like this, but not where it's pointing. But the quaternions tell you exactly where this is pointing, and here I have plotted with the continuous line the Z axis for the spacecraft, and the Z axis is important for, this is lunar flashlight. So it's like a CubeSat. Imagine the 6U, I believe, 6U CubeSat body here, and then there are solar panels. So there is like a cross of solar panels. And the way it worked is, if that's the sun, that's a bright light. So it tended to be flying with the solar panels pointed straight to the sun to collect the maximum amount of sunlight. That makes sense. But also it was spinning slowly around its axis, because that's spin stabilization. And we know that because of the quaternions. If we plot the z-axis of the spacecraft, and if we plot the location of the sun, as seen from the spacecraft, you can see it's mostly the same. So the spacecraft is tumbling slightly, it's not pointing exactly at the sun, but more or less. And I think I have something like, no, I don't have, but I have another plot which is the angular error. So how far away is it pointing from the sun, and it's just a few degrees. So this is what we can figure out with these quaternions, and it's quite interesting because it's information that it's usually not accessible with radio. With radio, sometimes you see fading on the signal. If the spacecraft is tumbling, then basically the antenna pattern, at one point it will be favorable for the ground station, at another point the antenna is shadowed, and you can see that this fading comes in with some period, and that gives you an indication of the rotation period of the spacecraft, but it doesn't tell you anything more. This paints the whole picture, and it's even more fun when you have both things. So when you have the radio signal and you can see the fading, and you're also able to decode the telemetry and see that the quaternions are describing the same kind of rotation which is causing your fading. We did that for one of the Artemis 1 CubeSats. I don't remember which one of them. So news about Hakuto. Peter told to us this morning, unfortunately, when it tried to land on the moon, it crashed. And Bochum was live streaming at the time. It was quite fun to see the official live stream. This had like a proper official live stream from the company, and also the AMSAT-DL live stream with the comments. But what we saw in real time was this, you see the carrier, and maybe you see in white here, it's like some thing which is parallel from the carrier, and if you look closely, it's getting away from the carrier. So when I was watching this live, I saw, hey, is that a reflection maybe from the lunar surface? That's unusual. And then signals suddenly stop, so that looks like no good. And controllers on the official live stream are like, hey, so the time is, this has landed yet, should we celebrate, should we not? And there was this weird period when no one was sure what was going on. Eventually, some days afterwards, The mission team did their own analysis. They published their findings. Basically, what happened is the spacecraft believed it was lower down than it was. So it was basically 5 kilometers, I believe, or something like that, above the lunar surface when it tried to descend smoothly, but it ran out of fuel. And there was some notion whether it actually had enough fuel to land or not. This is like internet gossip, not official information. But anyhow, Bochum had a front seat on this event, and with the information collected from Bochum, and again this is just the live stream waterfall video, and also with information collected by Ivan at home. This is a friend of mine in Catalonia in Spain. So he had a 1.8 meter antenna, I believe, and for collecting Doppler data is more than enough. He didn't see the reflection at all, which is maybe the most interesting thing here, because that's much fainter, but he did see the main carrier, and he saw some features with this image cannot be seen. There was some spinning, weird spinning, no one is really sure what went on. And we have a technical report. This is on AMSAT-DL webpage. James contributed to most of the technical part of the report, and also to put it together, the information from all these people, which was a good amount of work. So thank you, James, for that. What else happened? Assigning space. This was a project I participated in. It was an art project led by an Italian media artist called Daniela De Polis. And it was in collaboration with SETI Institute, ESA, and INAF. INAF is the Italian National Astrophysic something? Yeah, so they basically do radio astronomy observation in Italy. And what the art project was all about was taking an ESA spacecraft, actually TGO, Mars Orbiter, and transmitting to Earth a fake alien message. So better than fake, I should say composed by some artists. So the idea was to get people engaged in this experience and also discuss what would happen if this were to happen for real. If we ever received a message from an extraterrestrial civilization, would we completely freak out? Would we assemble to try to make some sense of the meaning of the message? What would happen? So it was an art project intended to try to see what happens even if we set all this up as some kind of global experience. And the way this worked out, the message was uploaded to TGO sometime in advance, and at some date we picked, it transmitted the message with the rest of the usual telemetry. And this was recorded by the Green Bank telescope. This is the largest telescope on Earth, movable telescope on Earth. It's actually the largest fully steerable structure on Earth. So it's 100 meters, it's huge. Medicina in Italy, and the Allen Telescope Array with only 20 meter, so 20 of these 6 meter dishes. Those were the SETI stations that were officially involved in the event, because the event was actually, the artistic part of the event was planned for several years in advance. The technical part of the event was being planned for almost a year, but it was only announced publicly a week or so in advance, because the intention was, if this was happening for real, people will not get so much advance warning, it will just happen. So it was only this reduced group of observatories doing the official recording, but then what happened is, when the news came out, we did some spreading of the news, and Bochum and also two 13-meter dishes operated by the Spanish and Portuguese geodetic network joined this activity. with 1 week of notice, so they were on Sky recording signals, and with all of them, except for Estévez, which had some technical problem, the signals were good enough to decode the message. And what I like most about this activity is that a bunch of people who are not at all familiar with amateur radio, with spacecraft, with anything RF communications, anything we do, got direct exposure to this. What we published for people to have a go at was raw IQ recordings. So that was the beginning, raw IQ recordings. Then people went through the first signal processing, and eventually it came down to a 8 kilobyte file with a message or something like that. And that made it easier for other people to participate. But initially it was just RF. So you saw many people wondering and getting interested in how this works, what the signal, how all is done, and that's great for education and outreach. This is Peter, I believe, tweeting the reception from the 20-meter dish. So here you can see the sidebands with the data. And something else that has happened recently is stereo A inferior conjunction. That's the technical term for the fact that it was launched, it has come around the sun, and we're also going around the sun, and for the first time since launch it's back again close to Earth. So that makes it possible to decode the low data rate weather beacon with even a 60 centimeter dish at home. That has been possible during the summer and probably also right now. So many amateurs have engaged in this activity, which has been, by the way, Bochum's day job, so to speak, for many years now. And there has been a global effort led by Scott to get the data, because the interesting thing about the data is those are images of the sun, or part of the data contains images of the sun, and Alan, who's here, so you can ask him for all the details, and also Scott did some reverse engineering, some finding around of some obscure documentation and obscure Linux 32-bit only software, which is able to decode or decompress actually the images, which is something that, by the way, Mario was after for a long time, and no one from NASA gave him a means to do it. But now it's actually possible to do it. So this is actually a video, but I couldn't get it onto the presentation. What happens is the sun rotates. So if you image it for multiple days, you will see it rotating, and some of the sunspots here hiding behind this one coming in view. And with all the global coverage of the amateur radio community, assembling these videos was possible. So to finalize, I think these are more exciting times than ever for deep space activities in general, for amateur tracking, and more exciting things are coming. In fact, there was recent news that this is bad for NASA DSN. They have been under a lot of pressure. I think they have a swear jar in Australia where anytime something goes wrong, they will just swear and put some money in for whatever. And they used not to swear, so much stress during Artemis 1, the mission, the CubeSat, etc. So much more demand, that means much more missions, both public and private. Large facilities, as you might have seen from this presentation, play a huge role in what we amateurs can do by assembling, collaborating and organizing tracking from a large facility. But we need to remember this is just a hobby for us. It's not our work. So what happens is this takes a lot of dedication. There are some key events which are a one in and off chance. There is this probe landing at Mars. Okay, it's right now or never. And there's a bunch of amateur people trying to track. Someone needs to be operating the ground station. And I think there are some missed opportunities because we all have a life, so this takes a lot of work. And maybe we could get more people involved or more automation, both of them help. Basically reduce the workload on people so that we are able in the future to keep up tracking all these interesting missions, because I think the reason we track these is because they are fun and interesting to us. And also basically try to record the data in IQ if possible, because that allows more analysis, and share the data. I've been sharing the data in Zenodo. That's an online platform for research data, and so far no problems with complaints or whatever. So I think this is helpful for everyone. Thank you.
Oh, there was a question, please.
One question. Is the Hakuto, do you think it can be that before it crashes it started to spin or something like that because of the widening of this area?
Yeah, so we do not know for sure. What we saw is there's a phase before the crash on the surface where by the acceleration on the Doppler we are almost sure that it's in free fall, or mostly in free fall, meaning there was just no propulsion and plop. And during that phase, the carrier becomes wavy. On advanced data, it's easy to see that there is some spiral thingy, but it mostly looks like a double spiral, which is weird, we cannot explain. And also we are not completely sure where the antennas are located, because if you have this spiral, it's because the antennas are offset from the rotation axis. So then you get like this back and forth movement. If the antenna is perfectly on the axis, you get no spiral thingy. And also we do not know exactly what happened. So how would you put this torque on the spacecraft? The leading theory is, well, maybe it ran out of fuel, but some of the engines stopped before some of the others, and then that caused some imbalance and it went spinning. But it's just not enough data to be sure what happened. Yeah, that is certainly possible, but I'm not sure if they would want to do that, because if you run them at the same frequency, then you usually get interference between them. So if you have two antennas, you use two different frequencies. That's a more simple approach.
I would like to add on this point, but we never officially said about it, but we sent all our data, we had the preliminary report and even the final report we sent to the proper people, because there's a propulsion team in Germany which was responsible for building, not for designing these things. They built the propulsion system. So thanks to us, they already knew what might have happened. The good thing is they were not responsible for the design, somebody else. But anyhow, the information was very welcome, even by the Japanese. They sent our report also to the Japanese, and it was very welcome, and really always with the intention, okay, next time we will look again, and maybe you can give us some information in advance, which makes tracking easier. One of the problems with many of those missions, as you mentioned, there is no trajectory data available. With Bochum, with this very small beam bandwidth of 0.01 degree, it is very difficult if you don't know where the spacecraft is.
Okay. I think there's no other question, so we will say thank you for your speech.